I have one more example, which is the instrumentation amplifier, and then hopefully this will be the end of today's lecture. This is also something that I gave you as a homework for your homework number 4. I know a couple of you have already done it, but I just wanted to look at another instrumentation amplifier as an application of op-amp, and then because we have exam coming up on Thursday, and everything that's going to be on exam is going to be related to operational amplifier. I thought of doing one more example where we drive an equation for the output voltage, applying KCLs and KVL and loop equation and applying Ohm's law, and then finding the gain. So what is happening over here? What is an instrumentation amplifier? Okay, so let's focus on the wording here. The instrumentation amplifier is one kind of differential amplifier. So it's a kind of a differential amplifier. And actually, if you look at this part of the circuit, maybe, okay, I don't know if you guys see it, but this part of the circuit is basically a differential amplifier, right? On the right, in the yellow lines. What do you see in the yellow lines over here? Blue lines over here. What kind of circuit are these? What kind of op-amps are these? We just learned about this also today. So anytime you see a circuit and you see that the output is directly just connected to the, a negative terminal, you consider it as a voltage follower or a buffer, okay, which has a unity gain. So you have and anybody remember from last lecture, why do we use these buffers? The reason we use these buffers because they have high input resistance, so no current is flowing through it, and then they have low output resistance, so I can connect the output of these buffer to some kind of high load, which may draw as much current as it may need without having an impact on the voltages at these terminals. Okay, so that's one of the reasons that we use the voltage buffers, also known as the a voltage follower. Okay, so these kind of circuit, they provide very high gain. They have high CMRR, so that's the advantage here. High CMRR, high input impedance, and it is designed for very specific application. It is used in certain industrial applications to amplify the output of the transducer and test and measurement equipment. Also, remember folks, it's kind of a critical in a way that because these are difference amplifier, so they may have some common mode rejection ratio. Okay, they have some common mode input signal. Okay, and if you remember, the gain equation for the difference amplifier was R2 over R1, V2 minus V1. If these two voltages, they have some kind of common mode signal, say some kind of noise or electromagnetic interference, they will also be magnified, right? This is a beta factor. So you want to make sure that that common mode signal is rejected and only the pure difference between these two input signals is magnified. Okay, so that's where instrumentation amplifier comes in real handy, and this is actually what you're doing in the tomorrow's lab also. Okay, so a few more basics about this instrumentation amplifier. The differential input will be amplified and common mode signal will be rejected, as I mentioned. This amplifier, the graphic that you see, it basically comes in packaging. Okay, this is one chip. This is you can think of it as one chip. Okay, these are the pins of that chip. Everything that you see over here, RF, R1, R6, R3, R4, R2, everything is inside this chip, okay, except for this RG over here, okay? And with the help of this RG, we can change the gain of this amplifier, okay? And that's what we are striving to do here, get an equation where we can change the gain as a factor of RG, okay? All right, so a couple of assumptions that we are going to make here before we start doing the analysis. If R5 and R6, okay, this resistor and this resistor is same, and the ratio of R2, R1, R3, and R4 over R3 equals to R2 over R1, then the data sheet says then output voltage is equals to 1 plus 2R5 over RG times R2 over R1 VA minus VB. Okay. And our goal is to strive for an analysis that helps us identify, okay, how did we get this equation? Okay. Now, few things that we should look at looking into this circuit over here. And that is the voltage over here is going to similar to what we have over here, correct? So the voltage over here will be the same that we have over here. I'll say VB, correct? Similarly, the voltage over here will be the voltage that I have over here. So I can say basically this is my VA, correct? Also, I'm going to say the voltage over here that I have is VB bar. And then the voltage I have over here is VA bar. Now, if I ask you, remember you have to keep this thing in your mind that the gain, the output voltage equation for the for the differential amplifier is V naught equals to R2 minus R2 over R1 divided by the potential difference, which is the V2 minus V1. Okay, remember that we have done this last week. Okay, now if I ask you guys what is going to be the value for the output voltage here, V naught, considering that here you have VB bar and then you have VA bar, what would be the value for V naught? You're trying to find out V out, the equation for V out, VO, and this whole thing is a differential amplifier, and the equation for the output voltage for differential amplifier is given here in the yellow box. What would this be? Come on, guys. Okay, what would be beta here? What would be the beta factor here? R2 over R1 for the differential amplifier. What was the beta factor? R2 over R1. This whole thing is a beta factor, correct? Right. So because I already have R2 and R1 here, I'll just simply write down R2 over R1. Okay, bracket open. Then we have V2 minus V1. What is that over here? What is that potential difference? The difference between the two voltages in terms of the variables. Remember, this VA is connected to the positive terminal. This VB negative is connected to the negative terminal. Okay, so these two are the input source. You know, you could just think of that this part of circuit does not exist for now. You only look at the yellow box, okay? And I can say this is kind of like some input signal, and I'm gonna say VB bar, and this is also some kind of input signal, and I'm gonna say this is some VA bar. So what would be this form here in this equation for the instrumentation amplifier? Positive here, negative here. Focus on that. If I say VA bar minus VB bar, will that be okay? If I say VA bar minus VB bar, will that be okay to say that? Yes, it will be okay to say that. So I'll just write it down, VA bar minus VB bar. VB bar, that's the output voltage equation for the instrumentation amplifier. And I'm going to say this is my equation 1 over here. Okay, now can anybody tell me also, I want to, okay, all right, now the question I have here, what is the current flowing in here at the input of the buffer? Yes, folks.
Zero.
Zero. There's no current flowing over here. There's no current flowing over here, meaning whatever RG, the current that's flowing across RG, is also the current flowing across R5. Is everybody following me? Because there's no current flowing here in this direction, means whatever the current is flowing across RG, because this becomes a series circuit then, right? This whole becomes a series circuit. In a series circuit, the current remains same. So whatever the current is across RG is also the current flowing in R5 and R6. And if I ask you, give me an equation in terms of the V over R for IG, what would that be? What is the voltage at these nodes? Let me rephrase my sentence. I'm trying to find IG here, which is the current flowing through RG. In terms of the expression, what would that be? The current across RG is the potential difference between these two terminals in red over RG, which is the resistance. So can anybody give me equation for that?
It would be VB minus VA over the sum of R5, RG, and R6.
Okay, now because I'm only interested in IG, So I just need to do RG over there. Okay, so VB minus VA over RG, and I'm gonna say that this is equation 2 over here. Now, because no current flows through input terminals of the op-amp, the same current flows through R5 and R6, which I already mentioned that. So I can simply apply Ohm's law here. Remember this VB bar here, right? And then this was the VA bar over here. So VB bar minus VA bar, okay? That is equivalent to IG times the resistance, and resistance is basically R5 plus R6 plus RG over here, correct? The current over here throughout this whole thing is IG. So I just simply apply Ohm's law to find out the voltage across these two terminals, VB bar and VA bar. Also, notice here, when we started this analysis, we assumed that R5 is going to be equal to R6, okay? So if I put that, I can write this equation, so IG equals to R5, and replace R6 with R5 also, plus RG, and then I can write it down as IG 2R5 plus RG. Now, also what I could do here is VB minus VA over IG. Yeah. So here I'm actually replacing IG with this equation, right? So IG is VB minus VA over RG. Okay. And then I have 2R5 plus RG. 2R5 plus RG. I can also rewrite this equation as VB minus VA, okay, and then basically multiply RG with this equation. So I get what? 2R5 over RG, and then when RG is multiplied with this, they both will cancel out, so I'll get 1 here. All right, let's move forward. Is everybody following me so far? Yes, folks? Everything following me so far? Okay. Yep. Okay, and also here, which is the potential difference, VD, because I have VB bar and then VA bar here. So this VD is basically the potential difference of these two, VB bar and VA bar. So I can write it down as VD equals to VA bar minus VB bar. Okay, and then this is equivalent to saying VA minus VB times 2R5 over RG plus 1, okay? Because this equation right here was VA bar minus VB bar, correct? So I can write it down over here, this equation, uh, like this over here, okay? And then what I am interested in is V naught. So if I rearrange this equation, I get V naught R2 over, what was V naught? V naught was this thing right here, correct? V naught was this thing over here. V naught equals to R2 over R1. So I get R2 over R1, okay? Times VA bar minus VB bar. VA bar minus VB bar is this thing over here. So I can basically put this whole thing over here below. So I get VA minus VB times 2R5 over RG plus 1. And if you compare this equation that we got here, is actually equivalent to what we had over here. And that's what we were aiming for over here. So it's just a simple analysis where we basically have a high common mode rejection ratio here. We can change the gain by changing the value of this RG and also this R2 over R1, and then doing that basically simply just calculating the V naught with minimal noise or any external interference that could be from the PCB board or could be any other thing. Okay. So this is your instrumentation amplifier. I wanted to go over that step by step. So this is how you would do it in the, this is what I would expect you to do in the homework for also. With this, I'm gonna finish this lecture today.